Okay, today we're going to talk about 1-5 complex numbers. We're going to use the imaginary unit I to write complex numbers. We will add, subtract, and multiply complex numbers. We'll also use the complex conjugate to find the quotient and write those answers in standard form. And we're going to find the complex solutions of quadratic equations. So some quadratic equations have no real solutions. If you remember when you're graphing quadratics, if you would graph that parabola and that parabola never touched the x-axis, we would say no real solutions. We would not say no solutions. And the reason we would not say no solutions because that's not true. It has no real solutions, but in fact it does have two complex solutions. And that's where the square root of -1 comes in. The square root of a negative number, in the past, we've always said, well, it's not possible. Well, it's not possible on the real numbers. It is possible on the complex numbers. The square root of -1 will be represented by the letter I, the imaginary unit, which means I squared would be -1. By adding real numbers to real multiples of the imaginary unit, the set of complex numbers is obtained. Each complex number can be written in standard form. Standard form is always going to take the form a plus bi, where a is the real part and bi is the pure imaginary part. Putting a real part together with a pure imaginary part, that gives us the complex number. So -5 plus the square root of 9. That can be simplified to -5 plus 3i. The square root of 9 is 3. The square root of the -1 is I, and that's where you get the -5 plus 3i. And that is written in standard form. Here's the definition of a complex number. Let a and b be real numbers. The number a plus bi is called a complex number, and that is written in standard form. The real number a is the real part. The real number b is called the imaginary part of the complex number. If b is 0, then a plus bi is a real number. If b is 0, then this would be gone. All that would be left is a. So that's why we have a real number. If b is not 0, a plus bi is an imaginary number because now you have an a and a bi. A number of the form bi, where b is not 0, is called a pure imaginary number. So notice if you have bi, there's no a there. So bi, as long as b is not 0, you will have a pure imaginary number. The set of real numbers is a subset of the complex numbers as shown below. So if I take all of the real numbers, which is everything that we've done before imaginary numbers, and add to that all the imaginary numbers, that gets us complex numbers, which means every number that you've messed with in the past has been a complex number because a real number is a subset of complex numbers. Any real number can be written as a complex number if b is 0. So if I was to write the number 7 as 7 plus 0i, that's what's going to make it look complex. So the imaginary unit, two complex numbers, a plus bi and c plus di, written in standard form. If those two are equal to each other, if I say that a plus bi is equal to c plus di, I'm saying that a and c are exactly the same, and b and d are exactly the same. That is the only way a complex number can equal a complex number. So if I had x plus 3i equals 4 minus or plus yi. If I had that written down, I said, hey, what's x? Well, all you have to do is look at it and say, well, x is the real part and 4 is the real part, so x equals 4. And y, which is the imaginary part, is the same place as the 3, so y equals 3. Okay, so that's what this equality of complex numbers is telling us. To add or subtract two complex numbers, you add or subtract the real part, and then you add or subtract the imaginary part. for the most part, treat I like it's a variable. If you treat I like it's a variable, you're going to be able to solve the problem almost all the way. And then we'll talk about different values of what what happens to I with different exponents later on. So if I wanted to add A plus BI plus C plus DI, A and C are being added. Those are my real parts. B plus D are being added together. Those are my imaginary parts that go with the I. Subtracting, make sure, I'll do the B's first since I've got the red one. I have B minus D, so there's my B minus D. A minus C, so there's A minus C. So again, folks, it's just like combining like terms. The additive identity in a complex number is how you get 0, just like in real numbers. The additive identity of a complex number, A plus BI, would be negative A minus BI. So if I had A plus BI and I added a negative A minus BI to it, I would get 0 plus 0I, which is 0. So let's look at adding and subtracting some complex numbers. 4 plus 7I plus 1 minus 6I. Well, I'm adding. So because I'm adding, really I can ignore the parentheses if you think about it. I have a 4 plus 1, which is 5. Then I have a plus 7I plus a negative 6I, which means plus 7I minus 6I. 7I minus 6I would be simply I, so my answer would be plus I. And that's the final answer. Can't do anything with that. That is written in standard form. My real part is 5. My imaginary part is 1I. Part B. Again, I'm adding two complex numbers together. We're going to treat the i's like variables. Because I'm adding, the parentheses really serve no purpose. I have 1 plus 3, which is 4. Then I have a positive 2i plus a negative 2i. Well, that's the same thing as 2i minus 2i, which is 0i. And that would be written in standard form. But I could also write that simply as 4. But in standard form would be 4 plus 0i to show that A is 4 and B is 0. Subtracting. Now all of a sudden the exponents are pretty important. I'd like to go ahead and distribute here. So I'm going to have 3i. I'll distribute this negative sign. So minus a negative 2 would be plus 2. Minus a positive 3i would be minus 3i. Here's a negative 2 minus 2. Here's a negative times 5i would be minus 5i. Combining like terms, I have 3i minus 3i. Well, that's nothing. Minus 5i. I'm going to write that second because I should have done the real part first to put it in standard form. Next thing I have is plus 2 minus 2. Those are my real parts, and those combine to nothing. So the answer in standard form might take the form of A minus BI. Of course, that's going to be the same thing as simply saying negative 5i. Part D, my first term and my second term are both added together, so I'm just going to ignore those parentheses as I do this. But I do need to distribute this negative sign. So to rewrite this, I have 3 plus 2i plus 4 minus I. Distributing the negative sign gives me minus 7 minus I. Combining like terms, let's do the real part first. 3 plus 4. 3 plus 4 is 7. Minus 7 is 0. imaginary part, I have 2i minus I, that would be I, minus I, that would be 0i, so plus 0i, or the answer to this one is 0. So adding and subtracting complex numbers, again, treat them like variables and you should be good to go. Many of the properties that we've dealt with in the past for real numbers also hold true for complex numbers. The associative property for addition and multiplication. Just a reminder, the associative property means if I've got a bunch of numbers added together and I got groupings going on, it doesn't matter how they're grouped. If the groupings change, it's okay. You're going to get the same answer, and that's when you're adding and multiplying. The commutative property. The commutative property for addition and multiplication says if I'm adding a bunch of numbers, order doesn't matter. Or if I'm multiplying a bunch of numbers, order doesn't matter. And the same is true with complex numbers. You can rearrange them and it's not going to change the value. And the distributive property over multiplication, over addition. You just saw me do that in the previous problem where I was distributing the negative sign. So we can distribute just like we do with real numbers on the complex set. Let's look at multiplying two complex numbers. Folks, this is a long, drawn-out process here, but if you'll notice at the bottom it says don't try to memorize this. Just know that if you're multiplying two complex numbers, you can multiply them just like any two other binomials. One little gotcha in there, and we'll talk about that in just a second. We've already talked about it, but I'll bring it up again. So let's go ahead and multiply this out by applying FOIL. First times first. First times first would be A times C, which is AC, plus outside times outside, A times DI. Well, that would be A DI, plus inside times inside, BI times C. That would be BCI, plus, that was my inside times inside. Last times last, BI times DI. That would be BD, but that I is being squared because you have that I times I. And I'm treating that I like a variable for right now. Well, this is where a little switch is going to happen. Because I squared, as mentioned a while ago, I squared is the same thing as negative 1. So what that's going to mean is that instead of having a plus BD here, this is going to end up being minus BD. Okay? And if you'll notice, I squared being negative 1, leaving me with that minus BD, that becomes a real part. So that is minus BD is part of my real. So let's look at my real parts. My real parts are AC minus BD. AC minus BD. Plus, my imaginary parts are AD plus BC. So AD plus BC, and there's the I. Now, if you want to memorize this, have at it. Have at it. I'm not going to mess with memorizing that. I just know that I'm going to apply binomial multiplication or whatever to get my answers, okay? Just by using the distributive property. Okay, part A, multiplying complex numbers. Part A, I just have a number 4 outside of a complex number, and this is going to be simply distributing that 4. 4 times negative 2 is negative 8. 4 times plus 3i would be minus 12i. And that is in standard form. Part B, that's a binomial times a binomial, so I will go ahead and FOIL this. First times first is 8 plus outside times outside would be 6i plus inside times inside, that would be negative I times 4, negative 4i, plus last times last, that would be negative I times 3i, or negative 3i squared. Remember, I squared is negative 1, so this plus negative 3i becomes simply plus 3. I will now combine like terms, starting with my real part. My real part is 8 plus 3, or 11. My imaginary part is going to be plus 6i plus or negative 4i, or 6i minus 4i, which would be 2i. And I'm done. You'll see that the way the text works it out, there's a lot of equal signs. They actually write out distributing the 2 to the 4, distributing the 2 to the 3i, and they actually write out distributing the negative I to the 4 and the negative I to the 3i. I'm just applying FOIL and working it as I go, okay? Again, if you want to see how the text works it out, go back and look at your notes. This document can be found by clicking on that link in your syllabus. I always think it's better to see multiple ways of working it out anyway, so seeing me work it different from the textbook is going to be a good thing. Okay, letter C. If you'll notice, letter C, I have 3 plus 2i and 3 minus 2i. If you think about the section that we did previously, that was called a conjugate. Well, this is actually a complex conjugate. I'm going to work it out, and you're going to see that just like conjugates with radicals, with complex conjugates, the outers and inners will also cancel. So working this out, first times first, 3 times 3 is 9, plus outside times outside, 3 times negative 2i is negative 6i, plus inside times inside, 2i times 3 is 6i, plus last times last, 2i times negative 2i is negative 4i squared. And just as I mentioned a while ago, because we're multiplying conjugates here, your outers and inners will cancel each other. Negative 6i plus 6i is 0. Also, notice here at the end, I have an I squared. I squared is negative 1. So negative 4 times that negative 1 becomes plus 4. I forgot my L for last, so I'll throw it in there real quick. Well, if negative 4i squared is 4, and I've already got a 9, and the inside's canceled, I have 9 plus 4, which is 13. So what happens here is I had a complex number. I multiplied that complex number by its conjugate, which is also a complex number. And notice that a complex number times its conjugate is going to result in a real number. And that's going to be important on simplifying as we try to get rid of real numbers. Get rid of complex numbers. Here we have 3 plus 2i squared. You can work it like it is. A lot of people don't like working it like this. I've seen people say, well, 3 plus 2i squared, that's going to be 9 plus 4i squared. They're not noticing the fact that this is a binomial times a binomial, which means we must FOIL. Okay? So anytime you have a binomial multiplied by another binomial, you need to FOIL it. So it might be beneficial for you to actually write out what does 3 plus 2i squared mean. And by writing it out like that, you're going to see that, oh yeah, that's a binomial times a binomial. I better FOIL it or I'm going to get it wrong. So first times first is 3 times 3 is 9, plus outside times outside, that's 3 times 2i or 6i, plus inside times inside is also 2i times 3, so it's another 6i, plus last times last, 2i times 2i is 4i squared. Well, again, I have an I squared. I squared is -1. 4 times -1 is -4. So that's to remind me that I need to change the sign on that. That is now a real part. So 9 minus 4 is 5. And then 6i plus 6i is 12i. Complex conjugates, I talked about this a moment ago. In that example, we had complex conjugates multiplied together. So anytime we have something in the form a plus bi times a minus bi, the final answer is simply going to be a squared plus b squared. So if you'll notice a plus bi, a minus bi, they kind of look like a difference of squares. But because we got that b squared, I squared, that -1 right here turned it into a positive, okay? So anytime we see a plus bi times a minus bi, all we have to do is take a squared plus b squared, and you'll be done. 1 second, let me go back. To write a quotient in standard form where c and d are both not 0, multiply the numerator and the denominator by the complex conjugate. So just like in the last section, we talked about rationalizing the denominator. We try not to leave radicals in the denominator. We also don't want imaginary numbers in the denominator. So if you have a imaginary number in the denominator, we need to multiply by the conjugate to get rid of it. So here's an example. 2 plus 3i divided by 4 minus 2i. Well, there's not really any type of a definition for dividing by a complex number. So instead, what we do is multiply by the conjugate of the denominator. So my numerator is 2 plus 3i. My denominator is 4 minus 2i. To get rid of the complex number in the bottom, we must multiply this fraction by a fancy 1. And this particular fancy 1 is going to be the conjugate of the denominator, which would be 4 plus 2i. And if I multiply the bottom by that, I must multiply the top by that. Multiplying the top out, first times first is 8, plus outside times outside is 4i, plus inside times inside is 12i, plus last times last is 6i squared. Divided by, well, because I have a complex conjugate, 4 minus 2i and 4 plus 2i, all I need to do is take my a, which is 4, plus my b, which is 2, and square each of those. Combining like terms in my numerator, remember I squared is -1, so this plus 6i squared becomes minus 6. Combining the real part of my numerator, I have 8 minus 6, which is 2. And then 4i and 12i is 16i. The denominator is 4 squared, or 16, plus 2 squared, or 4. 16 plus 4 is 20. Now, to write this in standard form, you have to have the a plus bi, okay? And I know this is going to reduce, but I'll reduce it in just a second. Because I have a single denominator with two different numerators, I can break this up into two pieces. I'm going to write this as 2 over 20 plus 16 over 20, and I'll put the I off to the side. Always, always, always reduce your fractions. So 2 over 20 becomes 1 over 10, plus 16 over 20. 4 goes into both of those. 4 goes into 16 4 times. 4 goes into 25 times. I. And there's your answer in standard form. You can write a number such as the square root of -3 in standard form by factoring out the I, because I is the square root of -1. So the square root of negative 3 is the same thing as the square root of 3 times negative 1, which is the same thing as the square root of 3 times the square root of negative 1, which will give you the square root of 3i. I want you to notice that I is not inside the radical. I'm going to rewrite this. If I had the square root of 3 times the square root of negative 1, I would write that as the square root of 3, and then put on I. I'd be a little bit more, obvious about where the I is. And you might also notice that when I'm writing a radical, I put a little tail at the end to show that, hey, it's closed right there. Anything to the right of this little tail is not inside the radical. So the square root of negative a would be the square root of a, I. Complex solutions of a quadratic equation. So here's a quadratic equation, 3x squared minus 2x plus 5. The quadratic equation is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And the importance of complex numbers comes into play because of that square root of b squared minus 4ac. This is called the discriminant. And we'll solve for the discriminant in just a moment. So remember, a quadratic takes the form ax squared plus bx plus c. So for this particular problem they've given us, I know that a is 3, b is negative 2, and c is 5. So to solve this, the way I always do it is I work that discriminant separately. So I'm going to go ahead and take care of that b squared minus 4ac. Well, b is negative 2 squared minus 4 times a, which is 3, times c, which is 5. Negative 2 squared is 4, minus 4 times 3 is 12. 12 times 5 is 60, and 4 minus 60 is negative 56. And so you can see that we have a negative number inside the radical. So start working this out over here. X is equal to negative b, negative 2, plus or minus the square root of, well, I already know that b squared minus 4ac is negative 56, all over 2a, 2 times 3. And we start to clean this up. Negative 2 would be 2, plus or minus the square root of, this negative 56. I know that there's a negative 1 in there. And 56, any perfect squares in that? I know 4 for sure. And that's going to be it. So I'm going to put times 4 because 4 goes into 56 14 times. All over 2 times 3, which is 6. Numerator, we have 2 plus or minus. Okay, taking some of the stuff out. The square root of 4 is 2. The square root of negative 1 is I. And the square root of 14 is just the square root of 14. So here's my square root of 14. And here's my I over 6. And to get that in standard form, we have 2 over 6 plus or minus 2 times the square root of 14 over 6i. And that's going to reduce to 1 over 3 plus or minus the square root of 14 over 3i. And remember, that is 2 separate answers to a quadratic. One of the answers is 1/3 plus the square root of 14 over 3i, and the other one is 1/3 minus the square root of 14 over 3i. Okay, and that is the end of this section. go ahead, as in normal lessons, stop the video here, work the practice problems on your own, and then come back and you'll see me work the practice problems for you. Okay, working the practice problems. Write the complex number in standard form. The square root of 25, negative 25, well, the square root of negative 1 is I, and the square root of 25 is 5. So the square root of negative 25 is going to be 5I. So the answer to that's going to be 2 plus 5I, and that is in standard form. Number 2, perform the operation and write the result in standard form. I'm subtracting here. So I'm going to have 7 minus I. Distributing the negative sign gives me minus 6 plus I. Standard form on the combined like terms, I have a 7 minus 6, which is 1. And then negative I plus I would be plus 0I. So that would be in standard form. So you can see that A is 1 and B is 0. The answer to that could also be written as 1. Number 3, I have a binomial times a binomial. I have 3 plus 9I squared. Well, to multiply that out, I have first times first. 3 times 3 is 9. Outside times outside, that would be 3 times 9I, which is 27I. Inside times inside is also 3 times 9I, which is another 27I. So I've got 27I for the outsides, 27I for the insides. Combine those, that gives me 54I. And then last times last would be plus 81I squared. 9 times 9 is 81. I times I is I squared. Remember that I squared is negative 1. So this plus 81I squared becomes minus 81. To write our answer, we would do 9 minus 81, which I think is negative 72, plus my 54I. And number 4, to write that in standard form, because I have a complex number in the denominator, I need to multiply the top and the bottom by the complex conjugate, which is going to be 6 plus 7I. So I'll multiply the top and the bottom by 6 plus 7I. Top, distribute the 2, gives me 12 plus 14I. The bottom is, because I'm multiplying complex conjugates, the answer is going to be A squared, or 6 squared, plus B squared, or 7 squared. So that gives me 12 over 85 plus 14 over 85I. 12 over 85 reduces to it doesn't, and 1485 also does not reduce, I believe. And since neither one of those fractions reduce, that is in fact the final answer. And folks, that's the end of the practice problems for this section. As normal, if you're struggling with anything, please contact me, email, text, call, whatever. I want you to be successful in this class. Y'all have a great day.